All right, let's call this part 3 of our trig derivatives, done on the practice section of that 3.5 packet. And these are the answer keys out there. You guys can find those, but I thought it'd be nice to work through a couple of them, especially those that get a little bit more complicated. So I'm going to pick a couple. Let's do it like the clean version. Let's take a look at 4 and then 5, and then down below, I think wouldn't be a bad idea to take on maybe number 9. And then we'll turn the page, let you look up the rest and request them as needed. I'll get back to you as quick as I can. So for number 1, that's like y prime. The derivative of the cosine is negative sine. The inside is 2x, you don't want to touch it, times the derivative of the inside, 2x, which is 2. Done. So it's the derivative of the outside with the inside untouched, times the derivative of the inside. Outside is cosine, inside is 2x. There's our derivative. A little cleaning, and we would get to negative 2 sine 2x. Clean and tidy, that's the nice kind. 4 is relatively similar in simplicity. So the derivative of cosecant, that's our outside, pi x is the inside. The derivative of cosecant is negative cosecant cotangent of whatever you had inside those, which was pi x. But don't forget to take the derivative of the inside right afterward and multiply it to this. And the derivative of the inside is just pi. So that's actually part of it. So to clean that up just a tiny bit, we want to put negative pi cosecant pi x times cotangent of pi x. Done. So getting the word out there. The next number 5 just has some layers. Again, you can pause, rewind, do as you needed. Again, sorry for some of the speed. I know it's fast, but digital does allow us a little bit of that. Y prime, you might think product rule, but really it's product is if you have two like functions multiplied together, and these aren't two functions. If that were negative 3x times tangent of 5x cubed, I'd use the product rule, but it's just a constant, and so a constant doesn't change the derivative. I'm just deriving the tangent and I'm multiplying it by 3. So there's something called the constant multiplier rule. If I've never made that evident to you, the constant multiplied to something you're deriving tags along. So watch. When I derive this, I'm really deriving tangent, which is secant squared of whatever I'm taking the tangent of, 5x cubed, times the derivative of the inside, and the derivative of the inside is 15x squared. Don't forget the negative 3 out front. It just tags along. Any constant you're multiplied to something you're deriving, you can actually remove it, do the derivative without it, and then multiply it back in when you're done, which I've done in this example. We could probably rearrange this a little bit. It already looks pretty nice, but I can pull the 15x squared out front with the negative 3, so we get negative 45x squared, secant squared 5x cubed, and those are some just nice chain rules, things that you would commonly encounter with a chain rule and trig derivatives. Number 9 has that weird thing where you want to remember to rewrite these. Sine cubed of x means sine of x quantity cubed. So it's a good time to think, ooh, yeah, I gotta watch out for that, because that is a chain rule that involves a trig function. The outside of this one actually is the 4 times something cubed. So it'll be 12 something squared. That something is sine of x, times the derivative of the inside is the second chain rule we've got to do, and the derivative of sine is cosine of x. So that's the number 9's tricky for its own right. And then it does ask us to evaluate it, so I thought it'd be nice to just bring up, here's that unit circle again, you might want to revisit it. We're doing pi over 4, and if you go to pi over 4, the coordinates give you the value of cosine of pi over 4 is the x coordinate, and it's the square root of 2 over 2, and the value of sine of pi over 4 is also square root of 2 over 2. So in each case, we're going to put square root of 2 over 2 into this for sine and cosine. So it's sine of pi over 4, quantity squared, and the cosine of pi over 4 not squared, that goes in there. And then when we evaluate it, we just know that this is the square root of 2 over 2. We'll square it in a minute, and this is also cosine of pi over 4 is square root of 2 over 2. So if you take and square that little chunk in the middle, we end up with 12. Squaring the square root of 2 over 2 produces 2 over 4, which is a half. That's kind of cool how it squares away the radical and leaves behind 2, but when you square the 2, it becomes 4. 2 over 4 is 1/2. And I didn't mess with this last part yet, but I just leave it for you. all in all, it looks like it's going to be 6. 12 times a half is 6. And then you take half of that again, that's 3 square roots of 2. Ends up being our final result. Okay, that gives a nice, just not all trig derivatives are as bad as the last ones I left you with. And then using it to find the slope of the tangent line is what evaluating means. We can still evaluate it with a little bit of knowledge of the unit circle, and hopefully that cleans things up for you. If not, maybe you confused it more, and please let me know. We'll jump to 10. Let's talk about some, if I see sine and cosine there, let's do simple ones once in a while, because they happen a lot. The derivative of 2 sine x plus cosine x. The derivative of sine is cosine, so it's 2 cosine. The derivative of cosine is negative sine of x. Done. Isn't that awesome? Just clean and easy. They get a little bit hairier when you have, some chain rule involved. So in number 12, there's a chain rule involved. So when I go to y prime of this, derivative of 5 is 0. The derivative of cosecant is negative cosecant cotangent. So it's negative already with the minus, but negative cosecant cotangent is the derivative of the cosecant chunk. But it's a chain rule. Remember, you have an inside function that we will have to derive at the very end. And while we're doing the derivative of the outside, we didn't touch that inside at all. Okay, so that's untouched. These negatives combine to make a positive. So when we're done, we'll put those back in together. But we don't forget we have to take the derivative of the inside, not twice because it appears twice, just it was the inside from the original I need to derive outside. And it might help to remind you, this is the same thing as 1/2 x squared. So if I write this differently, I'm deriving, or I want to erase a little bit more of that so you can see what I'm doing is I'm deriving 1/2 x squared is the same thing as x squared over 2. And that's easier in my mind because I bring the 2 out front, cancels with the half, x to the first is just x. But I put it all together here. 2 times a half is 1x. Voila, there you are. So the derivative of 1/2 x squared is just plain old x. Okay. Looks good, right? That's a good derivative. Handle that one. Well, cleaning it up might come in handy. It ends up being a positive x cosecant x squared over 2, so don't forget the negatives cancel, and so on like that. Number 13 might be one more to walk through. Again, the key's online. You can look through the rest of them if you like. But before I derive this, I'd want to make that tangent of 2x all to the 1/2 power, like that. And this is a double chain rule. There's an outside, which is the something to the half with tangent inside, and there's also a 2x inside a tangent function. So this is a double link chain. When I start, you just do one at a time. The derivative of the initial outside would be 1/2 to the negative 1/2. That's the power out front, reduce it by 1. Don't touch the inside. Times the derivative of the inside, and the derivative of the inside is derivative of tangent is secant squared. Don't touch its inside, right? But now we have to take the derivative of that inside, which is times 2. So just layers out. So all those layers, those chain links, it's the chain rule because it's like a chain of derivatives, a chain reaction of derivatives along the way. Little simplifying goes a long way with this one. The 2 and the half cancel, and then the negative exponents. So if I do this all in one fell swoop, maybe I might lose a couple of you. Would you let me know if that's the case? Because that's something I can definitely explain in more detail as time permits. A negative 1/2 power is the same thing as the square root of that tangent in the denominator. All right, to the next round. I want to get to another. Actually, maybe I'll just wrap this up as the third version of our trig derivatives, because the next piece I want to get into is the first derivative test. See you at that next video.